Welcome to Freeman's background material for Chapter 6, which is metabolism and mainly focusing on enzymes and the chemical reactions that relate to biology. We're going to start off today with an example of a couple of those enzymes, phosphatases and kinases. Phosphatase and a kinase just involve phosphate groups getting added to, in the case of phosphatases, or kinases, removing them from biological molecules. And sometimes that is for cell signaling, and sometimes that can be involved for some energy components as well. But we'll see some of these come into play next in our next unit when we deal with cell signaling and cell membranes. But I thought this would be a good example for us. You can see both the names phosphatase and kinase both end in the letters ASE. ASE means that the protein we're talking about is an enzyme. And an enzyme is a substance that enables reactions to happen more easily, sometimes more quickly, sometimes with less activation energy or less energy being put in to give that reaction a push. But it doesn't really change anything about the overall reaction, and the enzyme itself is not a part of the reaction. It's not a reactant, it's not a product, it's not used up by the reaction. So let's take a look, flip over to the notes. I'm going to skip kind of quickly through the notes that are provided by the book. So metabolism is the sum of all the reactions that are happening inside, inside both the cell and in an organism. And those metabolic pathways that we'll talk about, taking from molecule A and getting it to some useful molecule, maybe C or D, involves several different enzymes in that process. And enzymes help these reactions to occur without themselves getting used up. We've got a couple different types of pathways. Catabolic pathways is the breaking down of stuff. And the flip side of that is anabolic pathways. That's building things up and making bigger molecules. I like to think about anabolic steroids like bodybuilders. They're building up and getting bigger. Anabolic pathways are the same thing. We're taking small molecules and building them into big ones, like polymerization. And then the flip side would go back to catabolism, would be like hydrolysis is an example of catabolism. We're adding water and splitting things up. So let's see here. We're going to go through some background thermodynamic stuff. Energy is the ability to do work or the capacity to cause something to change. And the things that the forms that you are already familiar with from physical science and chemistry at least would be kinetic energy, potential energy. And when those two are exchanged between one another, like a kid swinging on a swing set, the energy doesn't seem to be present there forever. Eventually the kid comes to rest. You may have recalled people try to explain this with gravity. Gravity is not the reason that the kid comes to rest. The reason the kid comes to rest is because that energy has gotten transferred into thermal energy, and the energy's still there. It's just tied up in microscopic kinetic energy, basically. Like you, kiddo. Like the atoms or molecules in the air, in the swings, in the chains, in the top of the swing set where there's some friction there. All those things have warmed up a slight amount, and they possess all the original kinetic and potential energy that the swing set had. And heat, a lot of times people misuse this term, but heat is a transfer of thermal energy. Heat only goes from high temperature to lower temperature objects. For us to move something from a colder point to a higher temperature point, we're going to have to use some tricks and put in some other forms of energy to be able to do that. Let's flip along here. We've got a couple of other examples. We've got potential energy being stored. Gravitational potential energy is an easy one to think about, and we're going to use gravitational potential energy as a model for some of the reactions that happen. But chemical potential energy is mainly what we're talking about here. And your book makes a pretty darn good point about chemical potential energy. At the bottom of page 126, your book says, it's important to recognize that the breaking of bonds does not actually release energy. We sometimes think of energy stored in chemical bonds, and if you break them apart, you're going to get some sort of energy out. Really, in your book sums this up quite well. The phrase saying energy stored in bonds is just another way of saying there's a potential energy difference in the bonds that are currently there and the bonds that can be there with a different configuration. And when we reform those new bonds, we're going to have some energy left over. So that's kind of the long and short of what we're looking at with chemical bonds. With thermodynamics, we're going to look at energy and systems. When we talk about a system, we're talking about putting a box around a certain object and saying, that's the system. It can be an organism, it can be an ecosystem, it could be the entire planet. We could even say that there is an overarching system of the universe. Exchange between systems happens all the time. And the explanation of how that energy exchanges is thermodynamics. So an open system is one that's open to its surroundings and can exchange energy freely with the surroundings. And a closed system is one that is closed off and doesn't give off any energy to the surroundings, doesn't do any work to the surroundings, doesn't receive any work or receive any energy. So think about like an isolated system would be like if you took a styrofoam cooler, you put some sort of organism or object inside it and you sealed it up. Aside from maybe a little bit of energy transfer, that would be a nearly closed system. And you wouldn't expect an organism to live inside that for an appreciable period of time. Because organisms are open systems. We do have to exchange energy with our surroundings. And one of the reasons is thermodynamics says that even if we've got a certain amount of energy on the inside of there, we can't just hang on to it as usable energy and do processes that we define as life. Some of those processes, all of those processes, are going to generate waste heat. And that waste heat is not going to be useful for us. So the first law of thermodynamics says that law of conservation of energy. That's basically what the first law says. And there's no such thing as a free lunch. You can't get free energy. It also says energy can't be created or destroyed, even though matter and energy within the sun, or nuclear reactors, things like that. Yeah, matter and energy are really the same thing. So, second law of thermodynamics says that anytime we've got any process happening, no matter what, there's going to be thermal energy generated. And there's a certain percentage of that energy that is guaranteed to be lost as thermal energy. It doesn't have to be a lot. Some processes are rather efficient. But in biological systems, we're talking about a pretty appreciable amount of energy getting lost or turned into thermal energy that cannot be recovered for those living systems to reuse later on. A non-biological example would be charging up your cell phone in the wall. You plug in your charger, you plug in your cell phone to it, and you charge up your phone. You pay for a certain amount of electricity. A good portion of that electricity did not go into charging your battery and is not going to go into you actually doing stuff and sending and receiving information on your phone. It went into heating up the charger and heating up the phone battery, which you can feel when it's charging. Got a good picture of a bear there. Second law of thermodynamics says along with that there's going to be increased disorder or randomness of the universe, which also relates to kinetic energy at the microscopic level, or thermal energy being lost in the form of heat, being transferred from places where there's high temperatures and dissipating out until the thermal energy is kind of uniformly distributed throughout the universe. So that's what entropy is. It's a measure of disorder. If you want to explain like why your bedroom never stays clean, it's just natural. It's going to happen. Unless you put in a whole bunch of extra work to it, it will naturally become disordered. So spontaneous processes in chemical reactions are those in which the energy flow, or the change in free energy, I should put it, will be positive. There's going from reactant A to product B, we're going to have a net release of energy, kind of like a boulder flowing or rolling down a hill. Like, so let's say we got a hill here, we got a boulder sitting up on it. That boulder might be fairly stable there, but it can spontaneously slide or roll down the hill without anybody coming and putting some energy into it. So if its starting point is higher than its ending point as far as potential energy, then we say that's a spontaneous process. Your book again makes a really good point on page 125 here to say that spontaneous does not mean fast. That boulder, I went to Elephant Rocks last week. It was awesome. Saw some boulders that were way up high. Those boulders can spontaneously roll down the mountain and not be up on the very, very peak like they are. Does that mean they're going to happen quickly? No. It just means that the overall energy is already there for them to get down to the bottom. I don't have to come and lift the rock up. It's not, the opposite would be taking a boulder that's on the ground, taking some chemical that's at a very low energetic state, and then putting it in a condition where there's a lot more energy. That's the opposite of spontaneous, and those processes occur all the time too. Think photosynthesis. In dealing with disorder and order, we sometimes run into a little bit of debate as to where the energy is and how it's flowing into the system. So let's take a look at the picture here. So we've got some rather ordered things that occur in nature. The order inside our bodies is a pretty good example as well. Some people try to say that this order that we see in nature is a violation of the laws of thermodynamics because we're getting order from disorder. This starfish was not always, I don't know if it's a starfish, whatever that is, was not originally ordered. It took some things that were not in that nice, neatly organized fashion, and life put that into an organized fashion. This plant or cactus or whatever we have has organized molecules like carbon dioxide into really complex things like glucose and cellulose and amazing fibers. But these don't violate the laws of thermodynamics because we've got energy flowing into our ecosystems from the sun. The Earth is not a closed system. It is powered by the sun. Let's skip a couple more here. So we have relatively low entropy within us as organisms, and we do that at the expense of the environment. You are creating disorder in the environment so that you can live upon that change in order. Kind of neat stuff to think about. So we'll look at free energy in our next little video clip. Free energy is relating to the energy of starting reactants and final products, and whether we see spontaneous reactions, as in like exothermic reactions or exergonic reactions, versus endergonic or endothermic reactions.